explain using illustrations the change in pitch that will be observed when the source moves towards or away from the listener. And then number 3, we need to be in position to solve problems using this equation, the Doppler equation, where FL is equal to V plus minus PL and all of that. We shall look at either scenarios, the effect of the plus minus and what happens. Then we should be in position to also state the applications of Doppler effect in relation with the sound or any other application in that case. Then with the light, we need to be in position to explain the red shifts as well as the blue shifts. Just need to know what the blue shifts are and the difference with the red shifts. Okay, so our point of emphasis will be the red shifts, and then how do we use the Doppler effect to explain why we conclude that the universe is expanding. Okay, so that is according to our expectation as learners. We need to know at least all of that within that topic of Doppler effect. Okay, so we're saying that Doppler effect is basically a wave phenomenon that all of us have encountered in our everyday experiences. There's a physicist who first studied it in relation to sound waves, and that's where most of us have encountered it. So if a sound or if a source of noise, let's say an ambulance or siren, is coming towards you, you will notice that the noise sounds high-pitched. And then once that object passes you, then the noise drops. So that effect is under Doppler effect. So only for a split second, say when ambulance is right beside you, you do hear the sound in a way that is truly, and then same way that the driver will hear it. Okay, then they're telling us that, have you ever had an approaching fire engine or ambulance? And have you noticed the difference in sound of a siren? In this case, we can even use a train that is hooting. When it makes the noise as it's approaching, let's say a station, and then as it is passing by, the sounds will be different. Okay, so the difference in the sound, because you are standing, let's say, by the platform and the train is moving, or the train is standing and when you're moving and it's hooting, so that effect is what we're calling the Doppler effect. So there's going to be a point where we can represent the movement using the waves or using these sorts of circles to show that these concentric circles are moving towards each other, which means the object is moving in that direction. And then this way, it's moving away. Okay, we shall explain that further. Then we are saying that the Doppler effect with sound, you, the person that is hearing the sounds, are called the observer or the listener. So in my explanations, in most cases, I will interchange observer or listener. And then the thing that is emitting the sound is going to be called the source. Okay, you are going to be the observer or the listener, and then the sound source, where the sound is coming from, that's going to be our source. So as I mentioned next introduction, we have two situations which lead to Doppler effect. Number one, when the source moves relative to a stationary observer. So stationary simply means you are not moving, you're just standing in one place. Okay, so the source is moving, it's coming towards you. And then scenario number two, when the observer moves relative to the stationary source. So let's say an ambulance is making noise and then you approach it. What's going to be the difference? Then definition of Doppler effects, we're saying that Doppler effect is a change in the observed frequency of a wave when the source or the detector moves relative to the transmitting medium. I'll give you perhaps a simpler sort of explanation, but all we can say, sometimes we say it's the perceived change. Okay, we can say it's the perceived change, or sometimes we even call it the apparent change in frequency. Okay, apparent change in the frequency of sound that is caused by either the listener or the source that is moving relative to each other. It can be put out in very many ways. As long as you can just frame it and we have the word at least perceived or apparent change in the frequency of sound, and then we need to see the word relative motion between the source and then the listener. Okay, then below that we're saying that Doppler effect occurs when a source of waves and or the observer move relative to each other, resulting in the observer measuring a different frequency compared to what is being emitted. So the medium that the waves are traveling through, which is known as the transmitting medium, is also stationary in the cases that we're going to look at. In this case, we're going to look at sound traveling in space, and we shall assume that the speed of sound in space or air is constant. So the question that probably comes to mind is, how does the Doppler effect come about? Okay, so we can understand what is happening by thinking through the situation in detail. So case study number 1. If we have a moving source and then a stationary observer, so which means the velocity of the observer or the listener is 0, but then the velocity of the source is having a certain value. So they're telling us that if we consider a source of sound waves with a constant frequency and amplitude, the sound waves can be represented as concentric circles, where each circle represents a crest or a peak as wave fronts radiate away from the source. So this is because waves travel away from the source in all directions, and the distance between the consecutive troughs and crests in a wave is constant. So this is just explaining the circles that we saw in this scenario. The concentric circles moving towards and moving away. Then the next page they're telling us that we learned this in grade 10, and in the figure we have crests that are represented by the black lines, and then the troughs are being represented by the orange lines. Yes. Okay. But there were no colors there. Okay. So Doppler effect for moving source. So we're saying that if we have the long wavelength, the frequency is going to be very long. So from the wave equation, that is V is equal to F lambda. Okay. We know that if I make F the subject, it's going to be V over lambda. So which means frequency is inversely proportional to the wavelength. So if the frequency is high, the wavelength is going to be low. And if the frequency is low, the wavelength is going to be high. So this is what's happening. The long wavelength, low frequency, and then the small wavelength gives us the high frequency. So you can even see what is happening. So when it is moving towards, the circles tend to converge easily or next to each other with smaller distances. And if it's moving away, the distances between the consecutive circles will increase as well. And then how is Doppler effect explained? Remember we said using sound waves. We talk about the pitch, which is really just the frequency of a sound wave. So the more frequently sound waves hit our eardrum, the higher pitched the sound waves will sound. And then if we are headed towards the source of the sound waves, or it is headed towards us, then it will hit our eardrums more frequently, and that's why we shall hear a lot of sound or a lot of noise. And then the opposite is also true. So this guy experimented the sound to determine exactly how Doppler effect worked. And by listening carefully to the sounds made by a band as it played on moving platforms, he determined the size of what we call the Doppler shift. That it depends on how fast two objects are coming together or moving apart. Okay, so this is the formula that we normally use, whereby we talk about velocity of the listener, so the frequency of the listener should be equal to V plus say the minus velocity of the listener over v plus or minus velocity of the source, and then we multiply this by the frequency of the source. So we are saying if we're talking about the listener that is at rest, then the VL is going to be a 0. And then if the source is at rest, then the velocity of the source Vs is going to be 0. So this means that if neither the source nor the listener are moving, which means the frequency that the listener gets will be exactly the same frequency that is being emitted, since there is no apparent change in direction or movement between the two. And then what we're saying is that if the listener is moving towards the source, then the velocity of the listener is going to increase. Though if it's moving away, then the velocity of the listener is going to decrease, going to be less than 0. Alternatively, if the source is moving towards the listener, the motion is in the negative direction, and so on and so forth. Okay, I'm going to skip the examples for now and just look at the applications. Where do we find Doppler effect? Where do we use Doppler effect? So we have quite a number of fields where we use Doppler effect, and one will look at the medicine field or the field of science. How do we apply Doppler effect? So we have a machine that we call the Doppler flow meter. Okay, so this Doppler flow meter is basically the device that is used in medicine to measure the speed of blood flow. Sometimes we call it the rate of blood flow. Okay, so a transmitter that is placed on your skin sends out waves at a certain frequency, and then when the sound is reflected from the red blood cells, its frequency is changed due to Doppler effect. And then from the change in the frequencies, we can be in position to tell either how fast the blood is flowing or how close the body cells are. Okay, so it will be more of this. It will be having a transmitter, and then there has to be a receiver, so that when whatever frequencies are being sent out or waves are sent out, they bounce off the cells, and then the receiver will pick it up. It's more like even in submarines. Yeah. Okay. Then we're saying that a Doppler flow meter can also be used to detect the motion of the heart of a fetus as early as 8 to 10 weeks. Ladies that are pregnant, when you go for your scans, whatever science is used today is basically the Doppler effect. Okay, so in nature, they're telling us that a bat emits sounds with ultra frequency from its nose, and then when this sound is reflected by the insects, the bat can hear and can be in position to detect where the insects are. Same applies with the burglar alarms. When a person enters a room that is already sealed off, things will happen. Then application of Doppler effect with the radar. So we are saying that the radar gun uses Doppler effect to detect the speed of moving objects. So these are normally used by traffic cops when they are able to detect how you're overspeeding or you're breaking traffic rules along. So from a distance, they can be able to tell at what speed or what velocity you're moving, whether you're beyond the limit or below the limit. Then the last application is under the effect of light, where we explain the blue shift as well as the red shift. And so they're telling us that when a light source approaches, okay, when the source approaches, there is an increase in the measured frequency, just more like the sound. When the source of sound approaches, the frequency increases. And then we are saying an increase in the frequency is what we call the blue shift. Okay, why? Because the increase is towards the high frequency end of the spectrum. When you look at the 7 colors, I don't know, of the magnetic spectrum, is it something like that? Yeah, going to be red, orange, yellow, green, blue, indigo, and violet. You can play around with this. So towards this end of blue, we are saying the frequency is increasing. So that's going to be the blue shift. And then when the light source moves away from an observer, there's a decrease within the frequency. So a decrease in the frequency is what we call a redshift, because the frequency increases to the right. So on your left, the frequency is smaller compared to what you have on the right-hand side. So the end of the spectrum, and then we call that the red end. So this can be expressed just in this sort of format. So when the sound or when the lights move towards the observer, it's a blue shift. When it moves away, it's a red shift. Okay, and then from that, when you talk of the expanding universe, they are telling us that astronomers use large telescopes to collect light from stars. So atoms in the stars are in an excited state where they have a lot of energy because of the high temperatures. So this means that electrons in these atoms gain energy and move to higher energy levels within the atom, that is called the excited state. So from one energy level, which is lower, to an upper energy level because of the increased temperatures. So due to the absorption of energy, astronomers observe what we call the line absorption spectrum for elements that are present within the stars. What this means is that when these atoms have a lot of energy, the only way they can emit the excessive energy is by basically giving off the light. So in that case, we can be able to see the stars. So the analysis of these absorption spectra from stars indicates the presence of elements like the hydrogen, the helium, the iron, and other heavy elements. And then we're saying that the line spectra observed for these elements are similar to the ones that are observed on Earth, except for just one difference, is that the wavelength of the colors are a bit longer than on Earth. So all the colors have moved or shifted towards the red end of the spectrum, which means they are red shifted, which means they have smaller frequencies. So this type of Doppler shift results when the observer and the source of the light are moving away from each other. So as you move away, then the universe is also moving away, or the source of the light is moving away, then we shall observe a redshift. So the speed at which the galaxy is receding from the Earth can be determined from what we call the measured Doppler shift within the wavelength. Okay, so the phenomenon that the light from distant galaxies is redshifted was first observed by this astronomer within those years. Okay, then he found that light reaching the Earth from the distant galaxies is Doppler shifted towards the greater wavelength, and that is towards the redshift. So when the frequency is small, remember we said the wavelength is big. Okay, this led to the idea that the universe is expanding, and the redshift observed indicates that the galaxies are moving away from us. So guys, basically that is all I can say in as far as the Doppler introduction is concerned. Okay, so now I think it's time for us to just go and see what is expected of us, especially when it comes to some examples or worked activities. How do we approach the questions? How do we answer the questions? Okay, so if we have a question 1, an exam type question that is telling us that, should I start from here? Or I should start from the bottom? Doesn't make sense, does it? Does it? Yes, it's gonna make sense. I apologize guys in advance. Let me start from the bottom because I want us to start with baby examples and then we go deep. Okay, so with the first question, they are telling us that a bird that is flying at a constant speed emits sounds with a frequency of 90 Hertz. So which means the velocity of sound, is that the velocity? No, that is the frequency of sound, sorry. So the frequency of sound of the source is 90 Hertz, and then a stationary observer hears the sound from a bird at 88 Hertz. Okay, so the frequency of the listener is 80 Hertz. And then we know that the velocity of the listener or the observer is 0, since the observer is not moving. Okay, velocity of the source, we know it's moving at a constant velocity, which we don't know. Let's answer the questions. 10.1.1, they want us to state Doppler effects or Doppler effect in words. So in most cases, this will be the first question. Doppler effect in words. Remember we said we can state it in another way. So we are saying the change. So the change in the observed frequency. The change in the observed frequency, okay, of the sound detected, by a listener, because of the relative, we can call it relative velocity, because of the relative velocity between the source and the listener to the medium of propagation. The medium of propagation, of sound propagation. So guys, in any other way, for as long as you talk about, remember in the previous part we say the apparent change within the frequency that is observed by the listener as a result of relative motion between the listener and the source. Okay. Oh, I don't know, we can even put up a simpler definition, guys, where we can, let me just, I don't know why you're writing a lot of English here. Okay, someone can say that the change, okay, the change within the observed frequency, change in the observed frequency, okay, you can say when there is relative motion. When we have relative motion between the source and then the listener. I don't know, I feel that's a bit fancy. It's better. The change within the observed frequency when there is a relative motion, when there is relative motion between the source and the listener. So that change in the observed frequency. All right, so and then 10.1.2, they are asking us, is the bird moving towards or away from the observer? So when we look at the frequency that the source is emitting is 90 Hertz. When we look at the frequency that is being received by the listener, it's 88. So which means the listener is receiving a smaller frequency compared to what was emitted, which means the bird is flying away. Okay, and then They want us to calculate the speed with which the bird is flying. Okay, so from the Doppler equation, we are saying frequency of the listener should be equal to V plus or minus velocity of the listener over V plus or minus velocity of the source times the frequency of the source. Now, since we are having a scenario where the bird is flying away, how do we apply the plus minus? So since the frequency of the listener is smaller, okay, we expect the velocity at the bottom to be big, and then the velocity at the top to be small as well. So this can be reduced to frequency of the listener being equal to V. So since we want the top part to be small, we're going to subtract VL. And since we want the bottom part to be big, we're gonna add the 2, and then we multiply by the frequency of the source. So now we know that the frequency of the listener is 88 Hertz. Okay, I just substitute that. So this is our 88. What does the V represent? V is usually the speed of sound, okay, which is the 340 meters per second. So we can get that from the information page. And then we are subtracting the velocity of the listener. We say the listener is stationary, so that's a 0 over the velocity of sound waves plus the velocity of the source, which we don't know, times the frequency, which is a 90. Okay, then I'm just gonna go down. How do I play around with this? So I can do my maths. Okay, I know that this is gonna be 88 is equal to 340. I'm gonna multiply it by the 90 over 340 plus PS. And then I can do my cross multiplication. Okay, so that's gonna be 88 into 340 plus PS is equal to 340 times 90. I don't know, I don't wanna work that out. Then I'll divide by 88, divide by 88. I wanna punch everything at once in the calculator. So 340 plus VS is going to be, so when I punch that into my machine, into my calculator, that's gonna be 340 times 90, 340 times 90 divided by 88, it's giving me 347,72. Okay, I'll leave it at 73, it's fine, 727. Then I'll move the 340 to that side, which will be a subtraction. So 347,73 minus the 340. So I'm only left with 7,73 meters per second. So that will be the velocity at which, or with which, the bird is traveling. Okay. Oops. So that is done. All right. Then I'm gonna go to my question number 1. Okay, so question number 1. Question number 1 is telling us that we have an ambulance. We have an ambulance that is approaching an accident scene, still at a constant velocity. Okay, and then the siren of the ambulance emits sound waves with a constant unknown frequency. Okay. It's getting serious. So a detector at the scene measures the frequency as 1,07 times the frequency of the siren. What's going on here? Okay, so the ambulance is approaching, and so we have a scenario whereby the ambulance is approaching. Okay, so the accident scene is going to be like the listeners there will not be moving, so which means the velocity of the listener, I'm just going to leave it as a 0. The velocity of the source, the ambulance, is unknown, but we know that a detector, so this detector will be the listener at the scene, measures a frequency as this. So frequency of the listener is 1,07. The frequency of the siren is the source. Okay, we multiply that. All right, so state Doppler effects in words. So we said it's the perceived change, the apparent change in the frequency of sound caused by the relative motion. Okay, so we said it's the change in the frequency of sound that is caused by, we say, the relative motion of the source and the listener. Okay, then 1.2 there, I want us to calculate the velocity or the speed at which the ambulance approaches the incident. Use the speed of sound to be 340. So this is the main thing. Okay, so question number 1, since we know that the ambulance is approaching the scene, so from our formula, FL is equal to V plus minus VL over V plus minus VS times the F of S. Okay, so we know that since the ambulance is approaching, the top part is going to be big, the bottom part is going to be small. Okay, because we want the frequency to be more. The frequency that will be received is going to be high. So we know that our FL, from the summary, we said FL is 1,07. Fs, where there is FL, I can put 1,07. Fs is equal to this velocity V, which is 340. We are saying plus velocity of the listener is a 0 over the 340 minus, since this must be a small value, minus the velocity of the source. We are multiplying this by the frequency of the source. Okay, so for me, what I will do, I cannot have two unknowns. If a scenario like that arises, then I'll be having simultaneous equations. But in this case, since the information given to me does not lead to that, I'll cancel this and this. Divide both sides by the frequency of the source, since it's present either sides. Then I will cross multiply. So I can make that over 1. So I'll have 340 minus velocity of the source times 1,07 is equal to 340. Then I'll divide both sides by 1,07. I don't want to open the brackets because it's going to be quite a lot of work. So that is 340 minus Vs is equal to just 340 divided by 1,07. I'm getting 317. Okay, 76. It's okay. Then I'll move the 340 that side, so negative Vs is equal to, I'm having negative 22,24. Divide both sides by the negative 1, so the ambulance is moving at 22,24 meters per second. Okay, so that is that, and that is what is expected of us. Then 1.3, they want us to explain in terms of wave motion, okay, why the frequency detected by the detector is higher than the frequency that the source is producing. Okay, so we can say that the ambulance okay, is moving, ambulance is moving towards the detector or the listener. Detector, what's wrong with me, man? He's saying detector. The ambulance is moving towards the detector with what we call a constant velocity. Okay, with a constant velocity. But we know that lambda and v, velocity is equal to f lambda from that wave equation of ours. So if it's moving with a constant velocity, the lambda is going to decrease, okay, because it's closing in, it's moving closer to the source or to the detector. So we shall say that the wavelength decreases, and if the wavelength decreases, the frequency will increase. The frequency will increase. Or alternatively, someone can just tell us that since the ambulance is moving towards the detector with a constant velocity, we know that wavelength is inversely proportional to the frequency. So as the wavelength increases, the frequency decreases. But in this case, the wavelength is decreasing since the distance or its cover is getting closer to the scene of the accident. Then 1.4, they want us to state two uses of the Doppler flow meter. Now they are being specific. They don't want the use of Doppler effect. They want the use of the Doppler flow meter. Okay, number one, we said it measures the rate of blood flow. Rate of blood flow, we say the speed of flow. Okay, number two, we said it can also be used to determine whether arteries, is that the spelling of arteries? My apologies. Arteries are clogged or blocked. Okay, and then number three, we also say that it can be used to determine the heartbeat of the fetus, that unborn baby. I'm sorry if that's not the spelling, guys. So determine the heartbeat, okay, determine whether arteries are blocked, we determine the rate of flow of blood. So any two will be fine. And then 1.5, we're saying a line within a hydrogen spectrum is having this frequency when it is measured within the laboratory. But the same line in the light of a star has a frequency. Amen. What's wrong with you? Okay, it has a frequency of 7,23. Okay. Then the question is the star moving towards or away from the Earth? So before we answer this question, we need to look at the frequencies. This is 7,55. This is 7,23. So since the measured frequency from the lab, which is like on Earth, is 7,55, and then the same line in the light of a star has this much, what will be the explanation? So in this case, we're gonna say that this star is moving away. I'll choose away. Okay, what is the explanation? We're saying that light from a star, okay, light that is being emitted from a star is shifted towards what we call the lower frequencies, which is the red light. Okay, towards the lower frequency, which is the red light. So that is what we need to just say. So look at the two frequencies, and since the same line in the light of a star has a frequency of this much, so which means it's moving away. All right, question number 2. Question number 2. They are telling us that this person, Keenan, is standing at the top of the Leaning Tower of Pizza, accidentally, not pizza. I don't know whether it's pizza or okay, accidentally drops his cell phone when it starts ringing at a frequency of this much. The height of the tower is 56 meters. So shall I assume that the tower is straight upright, vertical, 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 not bent. Okay, then 2.1.1, they're asking us to calculate the speed of the cell phone at a height of 18 meters. Okay, let's say this is our 18 meters by using the law of conservation of mechanical energy. Oh, this thing is also here. Okay, so one thing that we know about mechanical energy is that it is conserved just from the law of conservation of energy. Mechanical energy is conserved, it will be the same. So at the top, it might be only the gravitational or the potential. Then at the bottom, it could be just the kinetic. But within the middle part here, it's both kinetic and then the potential. Okay, so what we're going to say, we shall say if we have the EP plus the EK, okay, at 56 meters, the energy at that height of 56 must be the same as the energy at the height of 18 meters. So the EP plus the EK at 18 meters. Okay. Now, one thing we know is that at the 56 meters, when this person is having their cell phone, that cell phone is having no velocity at all. From our formulas, we know that AP is mgh. The EK is a half mv squared. Now, since there is no velocity at this height, which means this EK is going to be a 0, and the cell phone is going to have a maximum EP. But this maximum EP will now be transformed into EP and EK, which must be equivalent to both that. Okay, so we're saying this side we shall have the mgh plus their half mv squared. The question is asking for the speed, which is the v. When I do my substitutions, that's a 0. I don't have the mass of the phone. We never mentioned anything. Okay, so what I'm gonna do, since I have the masses everywhere, I can just divide through by the masses. So this is gonna be mgh plus the 0. It's okay, I'll just do m into gh plus a half v squared. Okay? So that this m cancels that m, and then my gravitational force is, that's acceleration due to gravity, that's 9,8. Our height is 56, is equal to this gh, which is 9,8, but then at the height of 18, then plus a half v squared. All right, then 9,8 times 56, I'm getting 548. Okay, 8. Then 9,8 times 18 meters, that is 176,4, and then plus a half v squared. And then I'm going to transpose this to that side. So 548.8 minus the 176.4 is giving me 372. Let me just squeeze it here. That is 372,4 is equal to a half v squared. So I need to eliminate the half So I'll multiply both sides by 2. Okay, times 2 times 2. That cancels that. So my v squared is equal to something, which is 744, 8. And then I'll need to get rid of the 2 by finding the square roots. Okay, so square root of that is giving me 27.29. That's gonna be meters per second. Guys, that's our answer. Then we move on to the next question. They're telling us that there is a lady that is standing at the bottom. Is this the name of the lady? I don't know, but the picture is for a lady. No? Okay, so that person is standing at the bottom of the tower and hears the phone ringing as it falls towards her. What if we ignore the friction? They want us to calculate the frequency of the sound that is observed. So we need the frequency of the listener. We know that the frequency of the source was 490, if I'm not mistaken, 497 times 10. Okay, it's 497 times 10 cubed. Okay, times 10 to the exponent of 3. Okay, so calculate the frequency of the sound observed by this lady when the phone is at a height of 18 meters above the ground. So one thing we know that at the height of 18, what is the velocity of the source? We said it's 27.29. Velocity of the listener, they're just standing, so they don't have any velocity, so it's a 0. And then we know that our V is 340. Calculate the frequency of the sound observed. So we need the FL. So we need to do the substitution. We need to get our formula V plus minus VL over V plus minus VS times the frequency of the source. Now, since we're looking for that, okay, it's very ideal. So that is FL. Let's do the substitution. Now, since this lady, or since the phone is getting to the lady, so which means the frequency is going to increase. And when the frequency increases, one thing we know for sure is the top part is going to be big, and then the bottom part is going to be a little lower. Okay, so that's gonna be V plus, and then down we shall have the V minus. So that is 340 plus the velocity of the listener, which is a 0, over 340 minus velocity of the source, which is 27.29. And then we multiply this by the frequency of the source, which is 497 times 10 cubed. Okay, so when I punch that into my machine, that's 340. We're dividing it by 340 minus 27.29. Close that. 497 times 10 cubed. Guys, I'm getting a very big answer. How do I write that? Okay, I'm having 540,372.87 hertz. Okay, so I can leave it like that, or I can write it in scientific notation. This 1, 2, 3, 4, 5. So 5.40 times 10 to the 5 hertz. Either way, you can leave it like this, or you can whichever one you want. Then 2.1.3, explain in terms of wavelength and frequency why Kenan, who is at the top of the tower, observes a lower frequency of sound than the value that is calculated in 2.1.2. Okay, why does he observe a lower frequency? So such questions, we will go back to that wave equation where we say the phone is moving away, the phone is moving towards, so the frequency is inversely proportional to the wavelength. So we can say that the phone is moving away from this gentleman, Okay, who is not even making an effort to move. So this guy is stationary. Okay, he's stationary. And then we know that increasing the distance or increasing the wavelength, so distance is more like wavelength, leads to a decrease. Leads to a decrease in the frequency. Okay, leads to a decrease in the frequency. We can say since frequency is inversely proportional to wavelength. Okay, I believe that's enough. You have your equation, you have the explanation. What's happening to the phone and how does the moving of the phone work with wavelength and frequency. So guys, that's that. Okay, then 2.1.4, how the frequency of sound that is observed by the lady at the bottom compare at the height of 18 to that at the height of 3 meters, right? Only higher or lower. So since at the height of 18, there is a certain frequency that we had. But then this 3 meters is way closer to this lady. So which means the frequency must even be more higher. Okay, so the frequency is gonna be higher since it's moving more closer. Then 2.2. Okay, here we have the radar. So the speed cameras determine the speed of a car by measuring the signal of the radio wave reflected by the car. Explain why the speed camera cannot measure the speed of the car accurately at the moment the car passes the camera. Okay, guys, what do we say? What do you think? What do you think? So we're saying that the observed frequency, no? We know that the observed frequency will be the same as the original frequency. Original frequency. And remember, we're talking about speed, not frequencies. Okay, so the frequencies are going to be the same. The observed is the same as original frequency of the source. But the reason as to why it can not measure accurately is because the car is in most cases moving perpendicular, or the camera is perpendicular to the car. The car is moving perpendicular to the camera. I mean, the camera is placed right on top and then the car just passes below. So there is no way you're gonna measure accurately. As much as the frequencies, yes, they might be the same. And then 2.2.2, what is the speed of the radio wave in air? And give a reason for your answer. Now we know that radio waves are part of what we call the electromagnetic waves. These are basically waves that travel in vacuum and air, and they are more like light waves, or basically light. You can put it that way. So the speed of any wave that is under the electromagnetic spectrum, those different waves, the infrared, the radio waves, the TV, the micro, and all of them, they use just the same speed, and that is the speed of light. So that will be 3,0 or 3 just times 10 to the 8 meters per second. Usually it is the same, constant. Okay, they give, oh, they ask for a reason. So what is the speed, and give a reason. So it's 3,0 times 10 to the 8 because we know that the radio waves are electromagnetic. They form part of the electromagnetic wave spectrum. Then question number 3. Guys, let's push. Question number 3. They are telling us that the siren of a stationary fire truck emits sound waves of frequency this much. A car that is traveling on a horizontal road travels at this speed, passes the fire truck and continues. Name the medical instrument that makes use. Medical. So this must be a Doppler flow meter. Okay, Doppler is double P. That is a Doppler flow meter. And then 3.2, they're asking us, how does the pitch of the siren heard by the driver of the car change when the car is moving? Now remember, the fire truck is stationary and it's busy emitting sound everywhere. So, which means as the driver is approaching, it's going to be high. And then as the driver is leaving, the frequency is going to decrease. Okay, so we're saying, how does the pitch? Say pitch and frequency, like brother and sister. No? Okay, so when the driver is moving towards, that's gonna be, is it high or they said increase? What's wrong with me, guys? Okay, so we are saying it's going to increase. Okay, and the moving away, it will decrease. And then 3.3, they want us to calculate the frequency that is detected by the driver of the car, not the engine, of the engine truck. Okay, the driver, as the car moves towards the fire engine. So what is the frequency of the listener? Do we know it? It's what they want us to get. What is the frequency of the source? Frequency of the source, we said 1.8 hertz. Okay. The velocity of the listener, it was 30 meters per second. The velocity of the source is not moving, stationary, so it's a 0. They're telling us our V should be 330. Okay. What else? Frequency of the source. No, man, this is frequency of the source, not the listener. Sorry. Okay, so we have all information. Let's get the formula. So frequency of the listener is V plus minus VL over V plus minus Vs times the frequency of the source. Now, since we expect the driver to have a higher pitch or higher frequency, then the top part is going to be more, and then the bottom part is down. So frequency of the listener is going to be V. Now let me do the substitution, guys. Let's do the substitution. So it's 330 plus the velocity of the listener, which is velocity of the listener. Okay, it is 30 over the 330 minus velocity of the source, which is 0. Then I multiply this by the frequency of the source, which is 1.8. I can put this in brackets so that it will be easier when I'm using my calculator. So 330 plus 30, okay, over 330 times 1.8. So guys, that is giving me 1963.64 hertz when I round off. Okay, done. 5 marks. No? Then they want us to sketch a graph to show how the frequency of the siren changes as a function of time as the driver approaches and then the driver leaves. So this is frequency, and this frequency is measured in hertz. No? And then we can have this as our time in seconds. Not a big deal. So we know that as the driver is approaching, the frequency is going to be high. And then at that certain instant, as soon as he leaves, the frequency is going to go down. So this is all we need. Frequency was high, then the frequency is down. We're good to go. Question number 4. Number 4. They're telling us that a whale swims directly towards a stationary submarine at 8 meters per second. The sonar system of the submarine has a frequency of this much. Take the speed of the sonar wave in seawater to be this much. And then they want us to define Doppler effect. Guys, I'm not going to answer that. Remember, we said it's the change in the frequency of the sound detected by the listener because of the sound wave or the sound source and the listener having different velocities, or the apparent change in the frequency that is observed due to the relative motion or relative motion of the observer and the source. Okay, then they're asking us, how does the frequency that the whale observes compare to the frequency that is sent out of the submarine? The submarine is emitting. Since the whale is moving, they say it's moving towards. What's going to happen? Is it going to be higher, lower, or stays the same? So since the whale is approaching the source, then we expect the frequency to be higher. Then they want us to determine the frequency of the sound wave heard by the whale. Okay, so the frequency of the listener is what we need. We know that the frequency of the source is 23,000 hertz. Okay. And then the velocity of the source, we have the velocity of the listener. Is it 8? It's having 8 meters. So it's the whale that is having 8 meters. And then the submarine, they say, is stationary. All right, FL is equal to V plus minus VL over V plus minus VS times velocity of the source. Now, since the listener or the whale is going to have a higher frequency, which means the top part has to be a plus. They gave us the V, the velocity of sound, the speed of sonar wave in water is 1435. So the V is going to be 1435. So that's going to be 1435 plus the velocity of the listener, which is 8, over velocity of 1435, velocity of the source is a 0 times the 23,000. All right, do the substitution, punch that into the calculator. 1435 plus 8 over 1435, and then I'm multiplying that by 23,000. That is giving me 23128,22 hertz. So that becomes the frequency of the listener. And then they are telling us that the Doppler effect is also used to monitor the movement of remote stars. During such a study of a star, it was observed that the absorption line of the red light, it moved to 688 nanometers. On the Earth, the absorption line of the red light is observed as 653. Okay. Then they're asking us, is the remote star moving nearer or further away from the Earth? And we must give the reason. So we can see that there is a decrease. This is 688, this is 653. If we look at what is observed here and what is observed here, someone can say there is a decrease when moving this way, or there is an increase when moving in that direction. Now, since it was just observed that the line is this, so this is like the observed whatever frequency or the observed wavelength. And then this is also the observed on the Earth. Okay, from the star this is what it is. And then from the Earth, this is what it is. So what we can say is that this star is moving away. So it's moving further away. And what's going to be the reason for that? We know that F is inversely proportional to wavelength. So if this is our wavelength, which means the frequency is going to decrease. So if we have this and we compare it to this, you can see that this is going to have a smaller frequency compared to this one. So we can say that as lambda increases, the frequency will decrease. As the lambda increases, the frequency will decrease. If, and say if C is a constant, something like that. It's moving further away because the lambda increases, the frequency decreases. In this case, what was observed on Earth was this much. So it brings about a lower frequency. Then question number 5. Question number 5, they're telling us that light that was emitted from distant stars demonstrates the phenomenon known as the redshift. Okay. Explain how the phenomenon known as redshift can be used to explain the expanding universe. So in other words, they want you to explain what a redshift is. So we are saying that a redshift, this redshift implies that is emitted, that light from the stars, it shows a shift. Light emitted from the stars shows a shift towards what we call the lower frequencies of the spectrum. Light, this implies that light from stars shows a shift towards lower frequencies, yes, of the spectrum. That's correct. So according to Doppler, what did we say? So according to Doppler, you know that this means that the source, is moving away. As long as it's emitted towards the lower frequencies, it's moving away. So remember what we said, redshift, the source of light is moving away. Then 5.2, a submarine can use the Doppler effect to detect the speed of a ship. The submarine is at rest and just below the surface of water and detects the frequency of a moving ship to be this, which is 0.985 times the actual frequency of the sound that is emitted. Then the speed of the sound in water is this much. So is the ship moving away or towards the submarine? What's going to be our explanation for that? Now, when you look at what the submarine is detecting, it's detecting 437 Hertz. And they are telling us this 437 is 0.985 times the actual frequency. So since the number of times are less than 1, which means it's moving away, it is smaller. This 47 is smaller. 437 is smaller compared to the actual. So we're going to say it's moving away. And the reason for that is that the detected frequency is less than 1. can say it's less than 1 times. So 1 time the frequency of that, or the detected frequency is lower or less than, I can say the actual frequency. I don't know why you should use a lot of words. Okay, so our way detected is lower than the actual frequency because this 0 comma something tells us we're having something that is less than 1 time. Okay, then they want us to get the velocity of the ship. So velocity of the ship, we don't know. Is the ship the source? Yes. Velocity of the listener, which is 0, which is the submarine. The V, they told us it's 14 something, 1470. Okay. And then how do we get that other? So we can say frequency of the listener is gonna be 0,985 frequency of the source. I don't know, I can just use this the way it is, or I can do the substitution and get what I get. So which means I have the frequency of the listener, which is 437. I'm gonna divide it by that. So 437 divided by 0,985 is giving me 443,65. Okay, so you have the frequency of the source. And then, okay, I can do my substitution now. So I can say my FL is equal to V plus minus VL over V plus minus Vs. And since we said it is moving away, then the V is going to be a minus on top. So this must decrease, and then the bottom part must increase, and the Fs. So I don't know, I can use this new Fs of mine, or I can just use this equation the way it is. Yeah, let me use that. So 0,985 Fs. This V is 1470. We said minus the 0 over 1470 plus the Vs, which I don't know, times what is the frequency of the source. We say just Fs, so that this and this can cancel. Problem solved. No? Then we go into, we can do the cross multiplication. So we have the 0,985 multiplied by that. So in most cases, if you want to open the brackets, please do open. I don't feel like doing that because it's going to increase my workload. So 1470 divided by 0,985. Okay, 0,985 is giving me 1492. It's 1492,39. Okay, and then I'm just gonna subtract the 1470. And that gives me 22,38. Giving me the, so I have to move this side, so which means my Vs is 22,38 meters per second. So guys, that is the required velocity of the ship that they want us to get. Then 6, next 5. 5.3. Name 2 applications of Doppler effect in medical science. In medical science. So where do we use it? So remember we said to measure the rate of blood flow. Okay. And then 2, remember I said we can use it to measure or to detect any cloud or blocked arteries. And then we can also use it for scanning the fetus, no? Those scans that ladies go for. Doppler effect, remember I said. Okay, it can even be used to determine the heartbeat of the fetus. It's a whole lot of reasons. Guys, anything, as long as we get the marks. Then question number 6, what if we have graphs involved with waves? So a man mounts a siren, which produces a constant frequency of this on the roof of the car. He drives at a constant speed up and down a straight road while a stationary learner measures the observed sound. At a certain stage of the journey, the learner obtains the following pressure time. Okay. So the question is, this is our graph, pressure, time, and all of that. So from your grade 10, you should be knowing a trough, crest, and all the different features. They are asking us, what is the period of the detected sound wave? What is the period of the detected sound wave? Guys, what do we say? What do we do? The period of the detected sound waves. So we know that period is the same as the t, which is 1 over f. Okay. So if it's 1 divided by the frequency, in this case they told us this is the frequency that the siren produces on top of the roof, measured down a learner, and this is the graph. So times 10 to the negative 4. Okay, so 10 to the negative 4, what does it give us? 10 to the negative 4. I'm having 0,001. That's going to be seconds since it's period. Okay, and then they want us to determine the frequency. So from this formula, where we said period is 1 over f, which means the frequency must be 1 over the t. So that's going to be 1 over, what's wrong with me? So it's 0,0001 seconds, not a 5. Okay, so 0,0001, that's going to be, so 1 divided by my answer, I'm getting 10,000 hertz. So 10,000 hertz will be my observed frequency. Okay. Then they want us to state Doppler effect. We said we're not going to answer this. It's already up there. And then calculate the speed of the moving car with the speed of sound in this. So frequency of the listener. This is the listener over V plus minus PS times frequency of that. So we know that the frequency of the listener is what we just calculated up there, which is the 10,000. And then this is the 340 V. And since it's moving up and down, the top part is going to increase. So I'm plussing the learner who is a 0, the velocity of the learner that is observing, over the 340 minus the velocity of the source times the fs, which they gave us as 800. Then I'll do my magic. Start by, can eliminate the 800 over 800 over 800. That cancels. So I have 10,000 divided by 800, which gives me 12,5 is equal to 340 over 340 minus Vs. Do the cross multiplication. That's 340 minus Vs is equal to 340. Divide both sides by 12,5 over 12,5. So 340 minus Vs. Okay, divided by 12,5. I'm getting 27,2. And then when I move the 340 that side, then I get a negative answer. Okay, which is going to be 312,8. That is meters per second, which is a very big speed. Okay, then 6.5. 6.5. I hope I did the right thing, guys. Okay. While the car is stationary, the frequency of the siren is changed to 900. So they're asking us, will the wavelength of the detected sound increase, decrease, or remain the same? Remember, we're talking about frequency and then wavelength. One thing we know is that frequency is inversely proportional to the wavelength. Now, since it has moved from 800 to 900, which means the frequency has increased, so the wavelength must decrease. So the answer is going to be a decrease. You can say that frequency is inversely proportional. Inversely proportional to wavelength. You can tell us at a constant speed, constant velocity. Okay, now you can write it this way, or you can just use this equation, or you can use what we used in the first case where we say the frequency increases, the wavelength decreases, and vice versa. All right, so that is question number 6. Okay, let's have a question number 7 that is talking about the diagram below is showing a moving sound source. A moving source of sound, wave in air. It illustrates what we call Doppler effect, a phenomenon named after this scientist. And then 7.1, they want us to explain in words what Doppler effect is. Remember, we said it's the change in observed frequency as a result of the relative motion between the source and the observer. Okay? Now, when you look at 7.2, in which direction is the sound source moving? To the left or to the right? So one thing we said is that these concentric circles, where they are concentrated, simply means that is the direction of motion. Sound source is louder at that point. And then where the wavelength or the intervals are bigger, the frequency is lower. So which means the direction is left. That is to the left, since the concentrated part is on the left. If this thing was switched the other way around, then it would be right. So what happens to the observed frequency of the waves as the source is moving? So we are saying the observed frequency of the waves as the source is moving. So since it's moving to the left, the wavelength is going to decrease. Or the wavelength is decreasing. What happens to the observed frequency? Oh God, there's a wavelength. Yes, the wavelength is decreasing, hence the frequency increases. So the focus is on the frequency. What happens to the observed frequency? So that is going to increase. Then 7.4, they're telling us that a sound source is moving towards a stationary observer. Answer the following by stating whether the pitch increases. So what will the observer hear as the sound source moves towards? So this must increase because you're gonna hear quite a lot of noise or sound. That means the pitch is gonna be higher. Do they need reasons? No, they don't need any reasons. And then if it's moving away, it's going to decrease. And then if it slows down and stops, what happens? So if it is slowing down and then stops, which means the frequency is going to be the same. It will increase back to the normal as the source, then it's going to slow down and also stop. Okay, so it will increase back to the normal. Remember, it is coming, it's approaching you, so we expect it to increase, but it's not going to be higher than the original. So when it stops, then it will be back to the normal, that what you hear is what you ordered is what you get. Ne? Yeah. 7.5, the submarine is lying motionless, so the velocity of the submarine is 0. It detects a sound coming from a moving ship. So this is the listener. Submarine is the listener. This is the source. So we know that the velocity here is 0. And then the frequency detected is 1,003 times greater than the actual frequency that is emitted. So since this is greater than 1, it means the frequency is bigger or higher. The speed of sound in water is this much. Ignore the effects. Calculate the velocity of the ship. Velocity of the ship. There's no space there. Okay, so we know that frequency of the listener is equal to V plus minus VL over V plus minus VS times frequency of the source. Now, what we know, or from the details that we've been given, we know that the frequency detected, which means the frequency of the listener, is 1,003 times the frequency of the source. Does that make sense? The frequency of the listener is 1,003. Okay, so I'll say 1,003 fs is equal to my V, which is 1470. Since it is increasing, I'll have a plus. The listener is not moving. 1470 minus the Vs is what I need, times Fs. This Fs cancels that Fs. I'll do my cross multiplication. 1,003 times 1470 minus Vs is equal to 1470. Divide both sides by 1,003. 1470 minus Vs, 1470, divide by that much. So when I divide, I'm gonna get 1465,60. Then I need to move this to that side, which must give me a negative answer. That's 1470. So it's a negative 4,396. If I round that off and I divide with a negative 1, which means it's 4,4 meters per second. Okay, guys, that's question number 7. We're almost there. We are almost there. Question number 8. Question number 8. A man is standing on the sidewalk and notices that the sound of a racing car changes when the car moves towards him at a constant speed of 200 kilometers per hour compared to when the car is moving away from him. Assume that the speed of sound in air is that much. Name and state the phenomenon that is illustrated. Name and state. Okay, so for naming, yes, I'm gonna name it. I know it's Doppler effect. Okay, the apparent change. So remember what we said, the Doppler effect is the change in the observed frequency as a result of the relative motion of the observer and then the source. You can state that for us. No? Then 8.2, convert 200 kilometers per hour to meters per second. So this 200 kilometers per hour is the same as 200 kilometers divided by 1 hour. The negative one is the division. So which means we need to change or convert the kilometers to meters. We need to convert the hours into seconds. So we know that when we are changing kilometers to meters, we multiply by 1,000. I'm just gonna go the long way. Over when you're changing hours, converting hours to seconds, gonna be 1 times 60 times 60. So sometimes some people just have a quick rule of just either dividing or multiplying by the 3.6. Okay, so that is gonna be 200,000. I'm dividing it by 3.6. Guys, I'm getting 55,56. That is meters per second. So it's advisable, guys, to always convert to standard units. If you're given a question in kilometers per hour, please convert it to meters per second. And then they're telling us that if the frequency of sound that the man will hear when the car is approaching him is this much, calculate the frequency of the sound. Okay, so I'll reserve this for class. So we are saying FL is V plus minus VL over V plus minus VS times FS. We want to get the VS. We need the VS. So if I do my substitution, that is 298,84. This V, they tell us it's 340. 340. Yes, 340 with the frequency that we'll hear when the car is approaching. So if the car is approaching, which means the listener's frequency is gonna be high. So it means we have a plus. Velocity is a 0 since the guy is standing. Over 340 minus velocity of the source. They told us the car is moving. It's 200 kilometers per hour. We got that as 55,56. We multiply this by Fs that we need to find. All right, so we're gonna do the magic. Cross multiply. That's 298,84. I'm gonna multiply it by 340 minus 55,56. Can always simplify that. Is equal to 340 times the frequency of the source. Okay, so when I work that out, 298.84 times 340 minus 55.56, that is giving me 85002, having 0496 is equal to 340 Fs. Then I divide both sides by 340 over 340. So when I do that, I'm getting 250,00. So that is 250 hertz, since it is frequency. And then 8.42 uses of the Doppler flow meter in the medical field, we said, can be used to measure the heartbeat of a fetus, can be used to measure the rate of blood flow, and then we say detect whether arteries are blocked, and so on and so forth. Then question number 9, is this the last one? Oh Lord, yes, it's the last one, since question 10 is done. Okay, so question number 9, a police car is moving at a constant velocity with its siren on, passes a stationary listener. The graph below shows the changes in the frequency and all of that and all of that. Doppler effect in words, that is too easy for me now. No? We say the change in the frequency that is observed as a result of the relative motion of the observer and the listener. Then 9.2, write down the frequency of the sound detected by the listener as the car approaches. So we know that as the car is approaching, the frequency must be higher. Okay, so what frequency is that? So where the graph is starting from is 170. So that's going to be 170 hertz. And then the second part is asking when the car moves away. So the observed frequency is 130 when the car is moving away. And then they want us to calculate the speed of the car. Speed of the car. So we know that FL is V plus minus VL, V plus minus VS times the FS. We want the speed of the car, which is the source. So we know that since the frequency is going to increase, why are we saying so? Because in the scenario, a police car is moving at a constant and passes a stationary listener. It's either way. It is either way. You can do the 170 or the 130. For me, I'm gonna use the, I don't know, is there anything that I have? Let me see. The velocity of the speed car, I don't know. The velocity of the listener is a zero, frequency of the listener. I have two of them. Which is 130. Frequency of the source, nothing. So I have two unknowns, guys. So which means I have to use the simultaneous equations. Okay, not a big deal. Let's see. So with the first equation, if I use the 170, it's gonna be 340 plus the listener is gonna be a 0 over 340 minus the source times the frequency of the source. Okay. Is there a need for me to simplify this? It's okay, I can call this equation number 1. Then if I use the 130, that's when it's moving away. So this is towards. And then when it's moving away, it's gonna be 130 is equal to, there has to be a minus on top, minus 0, and then there has to be a plus down, and then times the fs. I'll call this equation number 2. Then what do? I can do the cross multiplication where I have 170 into 340 minus vs is equal to 340 times fs. I can make fs the subject by dividing by 340 on either sides. And then I'll do the same thing this side. So 130 into 340 plus vs. Okay, I'm going to divide it by 340. That is my fs. Okay, then I'll equate this fs and this fs. So I'll have 170 int 340 plus Vs over our 340 should be the same as this one, the 130 into 340 plus Vs over 340. Okay, and then what we do next, we can cancel this out since the denominators are having just the same values. Then we can open this up. You know that 170 times 340, that's gonna be 57800 plus 170 Vs. When I open that, 130 times 340, I'm getting 44200 plus 130 Vs. Something is fishy, something is fishy. What did you do? Your signs, your signs, your signs. My signs. This is a minus. Hey. Okay. So it's saying this is a minus, which means even you. Hello. Okay. It's a minus as well. Then I'll move this side, and then I can move that side. So it's 57800 minus 44200 is equal to 130 Vs plus the 170 Vs. So 57800 minus the 44200 is giving me 13600. Let me just copy something, okay? 13600. And then when I add 130 and then 170, is it a 300? Correct. That's 300 Vs. Then I'll divide both sides by 300 over 300. Okay, so divide that by 300, I'm getting 45,33. So Vs is 45,33 meters per second. So guys, it's possible that you can get a question like this with simultaneous equations. Please do not leave such marks. Just follow those steps. Use the two equations towards and away, and then apply what is needed. Then they're asking us that Doppler effect is applicable to both sound and light. We mentioned that at the start of the recording. It also has very important applications in our everyday lives. Okay. Name one application of the Doppler effect. We say the Doppler flow meter. Okay. Doppler flow meter. What does it do? Or what is it used for? You tell us what it is used for. We also mentioned something to do with the radar, whereby the traffic cops and what can measure the speeding cars and also issue tickets. Also mentioned about the use of the Doppler flow meter. We talked about the bats. We also talked about the burglar alarms and so on and so forth. The 9.5, use your knowledge of Doppler effect to explain the redshifts. So one thing that we said about the redshift is that this occurs when the spectrum of a distant star occurs when the spectrum of a distant star, okay, moves or moving away. What does it do? It emits. Let's say moving away from the Earth is shifted towards the red end, okay, of the spectrum. Or we say that it can also be structured by saying occurs when the spectrum of distant star moving away from the Earth emits lower frequencies, okay, lower frequencies, which means it's being shifted towards the red light of the spectrum. Guys, that's that. I think I'll stop there for now. Let's meet in the next chapter or in the next topic. Thank you guys. Please subscribe. We love you. Bye bye.